nice. Also, I want to just mention this work is not just done by me, so we've had various collaborators and students working with us on this. So Laura, Pedro, Nicole, and many more, especially Euclid. Sorry. Oh, okay. Yeah, sorry. One screen should work. Can I?
Yeah, so I think that's
Okay. Yeah. Okay. Sorry about that. So first, the outline of the talk. I'm going to present results from one paper, well, 3 papers which are already submitted. I'm waiting for reviews. Plus paper which was led by PhD student Pedro Cunha, who you can speak to about the machine learning club later on. And then a couple of other projects which where we did proof of concepts for machine learning methodologies, which we think can be useful within the context of Euclid, in the way that we try to improve estimations of galaxy physical properties. So lots of submitted papers in the last month or so. But of course, going back a bit towards the scientific context of why we're doing all this. So, I mean, basically, it's pretty clear that galaxies play a pivotal role in how we understand the general evolution of the galaxy, of the universe as we see it now. So from the Big Bang, more or less, right up to the current time, and I guess into the future if you're interested in that. And one of the main tools we have at our disposal are observations, and as such, large systematic observations of large galactic samples, both imaging and spectroscopic, are among the most crucial tools we have, most valuable tools for investigating galaxy evolution. So, of course, you're probably aware this kind of data allows a wide variety of investigations, from big statistical studies to very detailed studies of individual, special, or rare objects. And all of these fit within the overall context of what we're trying to achieve in astronomy. So, for example, the SDSS has been a particular goldmine of information about galaxy and evolution over cosmic time. And in the coming years, Euclid, along with various ground-based surveys, we think will play a similarly pivotal role in how we improve our understanding of galaxy evolution. So this specific work is motivated by the fact that with Euclid and other surveys, we'll have such a large number of galaxies and sources and quasars, etc., that they'll basically be, well, okay, it depends on how much computing power you have and what you want to do, but there's going to be too much data to really analyze everything using traditional methods, such as template fitting or other detailed traditional methods. So we need to find scalable methods to analyze this data. By scalable, we mean it works, let's say, at not much extra cost if you massively expand the number of sources that you apply it to. And so, in a certain sense, machine learning meets these needs, but there are some drawbacks that we need to overcome before we can really use it in a way which is competitive enough with template fitting. So, for example, we need to be able to derive high quality uncertainty estimations, either PDFs or just error bars, and other things as well, such as can you actually apply it to sources which of a type that your machine learning algorithm hasn't seen before. So machine learning is becoming more and more popular in astronomy. So I'm sure many people are, if not aware, have seen it discussed and seen papers appearing in arXiv. Basically, the type of machine learning which we're using here is supervised machine learning. So it uses labeled data sets to train algorithms to either classify or predict scalar values or labels of objects, basically. So this little fun diagram is showing more or less how it works. So you have the input data, and then the labels, annotations, which tell your model that these are apples. And then when you show the model an apple, it knows to predict that it's an apple because it's seen the characteristics before. So the great strengths of supervised learning is that once you've trained the model, classification or regression or labeling can be very, very fast on new samples. So to give you an example, we can, for example, classify millions of sources in a few minutes, for example. When with template fitting, it might take hours or weeks to do it or more. Another cool thing is that machine learning of this type can exploit hidden or complex relationships between, let's say, the observables and the labels. So things which maybe, there could be physics we don't know about, or there could just be relationships we don't know about, or structure, because either it's very complex, or let's say it's there in a very, let's say, hidden way. To contrast with that, the main weaknesses, of course, are that most machine learning methods, if they haven't seen something similar before, they have trouble classifying it or deriving properties. So this is kind of a problem if you have, say, you want to derive photometric redshifts, and you have some very high redshift sources, but they're very sparse in your data. So you can end up, let's say, having problems to actually either classify them or get redshifts for them. And also, there's no, at the moment, it's not that easy to try to, let's say, induce adherence to actual physical laws, which is also something else that we would like to be able to do to avoid, unphysical combinations of parameters. So, well, moving on to the first paper. So the idea was to test how well machine learning can select quiescent galaxies using mock Euclid photometry, sometimes combined with mock ground-based photometry, so simulating LSST or unions. And for this, we used 4 different data sets, which were made by Laura Pacicello. So basically, the 2 main methods. One is to basically interpolate from observed cosmos broadband magnitudes to try to make the Euclid bands. The other was to fit an SED, the galaxy SED, to the photometry, and just take directly from there. So they both have their advantages and disadvantages. We don't need to go into that so much now. And we try to make, of course, the data aligned with what we expected Euclid to give us in terms of sensitivity. So it's been a little bit of a change in that since we did the work, but I think the results are still very relevant. And so the labeling for this sample was basically a binary scheme where sources which have specific star formation rates in log less than minus 10.5 were defined as quiescent. And we tried to remove all AGNs by removing X-ray sources. If you want to read more about the catalog, you can read Laura's paper, which gives a very detailed description. And before showing the results, I guess we should look at the main data processing steps. So this is mostly standard, but there are a few different things we've done. So as I said before, we have a binary quiescent star forming target feature or label. Then we take all of the photometry and we compute all the broadband colors, of course, without repeating. Because what we want is we want the learning algorithm to have, in the most clear way, the full SED information. So every color tells you the shape of the spectrum in a way that's not so easy for it to obtain if you only give it magnitudes. But we include the magnitudes as well because this is also useful information. We also try to generate some kind of sparsity awareness. So, of course, in real data, you have missing values for reasons. Here, we just used one magic value to basically replace the missing values. So these can be basically cases where it's a dropout, or maybe the area of sky was observed in that band, or there was masked, or some other problem occurred. But basically, the concept there is that missing values, simply by being missing, carry information about the nature of the source in many cases. So I know that there's a debate about whether you should try to impute actual values or not, but this is what we've tried here. We also did a bit of feature selection, so we dropped columns which we found weren't that they don't improve results, basically. And we also dropped galaxies where there were too many missing magnitudes, because there's no point in trying to classify objects which have one or two colors. So this is the classification pipeline we used. So we start off with a photometry catalog. We do the picture engineering, pre-processing. Then we do a train test split. The test set isn't seen again until the very end, but the training set then gets trained on by 5 different what we call base learners. So these are different machine learning algorithms. So here we've used random forest, then LightGBM and CatBoost, and those are gradient boosting decision trees, which are a bit different to random forest, but we can go into that later. Then the k-nearest neighbors and a neural network as well. So they're trained separately on the training data. Then finally, we combine them into a single classifier. And we do that by using another machine learning algorithm, which looks at the results and tries to figure out how best to pick the best result. And it has complete freedom, so it doesn't have to pick the best result. It can take the average, or it can just find a pattern to choose, let's say, to determine the best value of the class. And then finally, we project final classes and we validate the metrics. So the classes come out, you get like a binary answer, 1 or 0, plus a value which is between 0 and 1, telling you essentially the probability of it being one of the other sources. But we also use XGBoost at high redshift because we kind of work better. But so these are the basic main results. So if you look at, so we're showing in different redshift bins the precision, the recall, and the F1 score. Precision is essentially the purity in astronomy. Recall is completeness. And the F1 score is the harmonic mean of the two. So I like the F1 score basically because it gives you a very general picture of how good the model is performing. But that all of those metrics are useful. So what we have there are 3 different machine learning setups, basically using different input data. So the blue line is the case where you have Euclid, optical, and WISE1, WISE2, and 20 centimeter data. So as you imagine, the WISE1 and WISE2 and the 20 centimeter are very sparse, but we think they are useful anyway. And that setup, of course, gives us the best results, the highest precision, recall, and an F1 score in all sort of cases. If we go with Euclid only, but we still know the photometric redshift, then we get similar enough results, although at the at the low redshift end, we start to see the performance degrading. And then if we go to the most extreme case, the black line, where we have only Euclid data and we don't know the redshift beforehand, basically the performance drops quite a lot. But in some cases, like in maybe the very bottom right plot, you can see at redshift 1.75, maybe there's almost not much difference between having the redshifts and the optical data and not having it. But otherwise, it's a lot worse. And then the green line is showing a color selection method from Larry Pizzagello's paper in 2020, which was using the Viz minus Y, the J minus H colors. So as you can see, the machine learning methods generally outperform the color selection. This is easy to understand because essentially the machine learning method has a lot more information at its disposal. It can learn how to weight the different colors in an optimal way to arrive at the best answer. Whereas with the color, it's more, there's only two variables there. And yeah, you're basically missing a lot of information. And we also thought it'd be interesting to see what happens if we compare our results with UVJ color selection and LePhare SED-fitting. So we were kind of surprised that machine learning methods quite strongly in some cases outperformed both of those methods, because LePhare basically has the same templates that we used to derive the original classes of this data. So we thought it should be able to arrive easily at the right answer, but somehow it doesn't. Somehow the machine learning methods are able to improve on it. This might just be the case where maybe it's important for having an automated reweighting of the data. So some colors are more important sometimes than others, and the LePhare method, I think, isn't doing anything much like that. Okay, quickly this. If you want to, within our pipeline, you can choose the say the decision threshold. So normally we say if an object has, say, a probability of higher than 0.5, it's class 1. If it's lower, it's class 0. But you can tune that depending on whether you want high purity or high completeness. So if you really want, you can have a sample of quiescent galaxies with very high purity, or you can have a very complete one. But it's hard to have both at the same time. So I've got the options there. And we also wanted to understand beyond the obvious ones, which observables are useful for selecting quiescent galaxies at different redshifts. And this is, I suppose, motivated by the fact that if we want to plan future surveys, we need to know which bands are going to be useful for our science. So here I've used the gain-based feature importances from ArXiv. This is an important distinction because the typical feature importance you get from, e.g., random forest, it's not really connecting the performance of the model to the way in which it uses the features. So yeah, imagine you have a tree structure with splits going down through it. You want to know not necessarily how often, say, a color is used to split it, but you want to know what the impact on the final performance of the model is from using that feature. And this is what XGBoost is giving us, basically. And there aren't many surprises there. You can see basically that the most important colors or bands evolves with redshift. So it's basically where the 4,000 angstrom break is shifting, more or less. But anyway, it's useful to see this. Something which was kind of curious is that we found that even though the features are very sparse, so most of it's missing data, the Ys and the 20 centimeter data also help at specific redshifts. So say redshift 0.5 and 2.25 maybe, having those bands gives a little improvement in the model quality. With the 20 centimeter, we're not really sure why, because these aren't necessarily radio sources, but who knows? I guess someone will eventually. So on to the next. Well, this is a work in progress, which we're actually working on right now. The concept here is that we want to test different machine learning methodologies for estimating galaxy physical properties. So photometric redshift estimations are very advanced. We've already had the Euclid Space challenge, which pulled out a lot of very nice methods, tested them. But we're now moving towards, say, going a bit deeper by expanding this to physical properties. So here I wanted to try out, or let's say prototype, a method which uses the CatBoost gradient boosting decision tree method in a way which tries to allow the right covariance between the labels. So, for example, you don't want to end up with, say, a mass and a star formation rate for the redshift, which aren't physical, or which would never occur together. So you want to get some kind of consistency. And with machine learning, that's quite hard to force. Basically, what the method does is, so hopefully it's not too complicated, but yeah, maybe in questions we can discuss more. So you start off with X, which is the training data, basically. So this is like colors and magnitudes. You train the first model on it, then you make predictions of your Y hat, basically, which is the prediction of the label. So this might be redshift or mass or star formation rate. And then what you do is you decide, okay, is that enough? Do I stop or do I carry on? And in this case, we carry on, we go background, and we take that prediction, we put it back into the training data, train a new model on that. So the next model sees the original training data and it sees prediction from the previous model. And next, your prediction, another physical property. And you do the same again. You build up a gradually larger training set, which includes the original the photometry bands, the colors, and the predictions. And then at some point you decide, okay, it's converged, there's no more improvement happening, and we take the final predictions. So what we found is that by doing this, we actually get an improvement in the quality or the metrics of the physical property estimations and the redshift. Let's say in a way which we hope also gives better consistency, better covariance between the final outputs. And what's interesting here is the more properties you try to predict at the same time, the better predictions of all of them become. So even properties which you don't care about, for example, maybe you don't care about extinction, this just trying to predict it alongside all the others helps you get better predictors for those other properties. Yes.
I like the idea to check which features are important and which redshifts. How did you do it? Did you train the models on data chunks split by different redshifts? So by using just a fraction of data in each subgroup, or there is a better trick?
So I have to actually remember what I did. It's like a year ago now. I believe here I split the data into these redshift bins, and then I did the binary classifications, try to classify into quiescent or star forming. I'm 90% sure that's what I did. So yeah, I hope that's enough of an answer. Okay, so of course you may be wondering, is it safe to put the how do I avoid target leakage basically? Yeah. Well, the key, we couldn't show it in this diagram, it's become very complicated, but we did cross-validation, well, k-fold cross-validation to basically generate out-of-fold predictions for the test set to make sure that nothing from the test, sorry, the training set, make sure nothing from the test set actually leaks into the model training. So yeah, that's the method. So these are just okay, sorry, something moved there. Sorry for the low quality of that plot. These are basically some early results. So here, this is applied to Cosmos 2015 photometry using these bands. I took an arbitrary cut at H24. I mean, that more or less matches depth that Euclid will go to, but the optical bands, the other bands, of course, don't. Yeah, and basically the results look, as far as I can see, okay, encouraging. It's nice that we can predict age and extinction as well, even though, of course, their plots look a bit funny because they're all quantized, because the ground truth is quantized. Our next step here will be to compare with other methods, compare with phosphorus, for example, to see exactly how good or bad this is. So I'm afraid that I can't tell you whether this is or not. So as part of this project, we needed to find a solution for the fact that these regression models don't standard give you reliable certainties on their output values. So we looked at different things. Actually, I have a small collaboration with guys in a tech startup who are trying to do a very similar thing, but I guess become millionaires rather than write papers. Basically, we both came to the same conclusion independently, that a good way of doing it is just to train a new model on the actual residuals. So essentially the difference between the predicted property value and the ground truth value. Train a model on that, and it thinks it's trying to predict the specific residual, but what it gives you is something like a 60% confidence interval error bar. So that gives you like a statistical like average, but it's still giving you an uncertainty specific to each specific object. So it's leveraging information from the whole data set. I'll wait for the place to go. So anyway, what I'm showing in these plots is when you plot the actual residual, the predicted error, we see that predicted error is, let's say, very, very close, statistically speaking, to 68% uncertainty percentile. With the redshift, there's a bit of an offset. We're not sure what's wrong there, but we're working on that. So basically, we're able to produce very, very quick. So these models take like maybe a minute or less to produce. So it's very fast. We can produce basically what appear to be quite reliable error bars. And leading on from this, what's interesting to try is if you're confident that you've got error bars for your test set predictions, even if you don't have the ground truth, you can then go and estimate what your model metrics are, basically, to know how good your model is performing, or let's say not know, but to estimate how good your model is performing on your unlabeled test data. And here actually you can see we're plotting the normalized median absolute deviation for star formation rate and mass. And you can see at the at least below ratio 2.5, the measured metric value and the predicted ones are almost identical. And you can see they have a kind of similar or a similar curve. Something goes wrong at high redshift, and this might be due to the fact that the original regression models aren't working very well for high redshift objects. But I mean, this actually is interesting. This opens the door to tuning or selecting models based on how well you estimate it to perform on your test set, which is a bit different to, let's say, the classical paradigm where you estimate or you tune your models based on some validation set where you have the labels already. Okay, next paper briefly. I'll also talk about the work from Pedro Cunha's master's project, which he published in A&E recently. So basically, the sheep pipeline uses machine learning to classify stars, galaxies, and quasars. So this was tested using SDSS and wide spectrometry. The idea was to see whether we could go beyond what was at the time state of the art of classification of those three types of objects. So the key thing here is that basically adding first estimating the photo Z, then including that as a feature in your training set helps, well, significantly to improve the classification of the sources. Well, here's the flow chart. You do the usual thing. You start with photometry, do some pre-processing, and then what happens is you have three different learning algorithms: XGBoost, LePhare, and CatBoost. They make their own predictions of the redshift, and then there's like this goes to a soft vote basically, and then that's combined with the original training data, and a new model is trained on that data. and then you get predictions. No, sorry. Then you go to the next stage, which is the classification. So here you have two possible branches. One is the one versus all approach. The other is multi-class approach. So it depends on exactly what you want to get out of it. What was kind of interesting here that Frederick found is that once you do, say, the one versus all approach, if you look for predictions which are uncertain, by this we mean the different models, the different one versus all models, if two or more give you a positive answer for one object. So, for example, the galaxy versus all model might say it's a galaxy, but the QSO versus all might say it's a galaxy as well. Then these are uncertain predictions. They go through to the right branch, where you have like a meta learner, which basically trains a new model to basically try to correct such individuals, correct the problem. And these go through the final predictions. If you want to take the multi-class approach, then what was found to be useful is to do a photos the outlier detection. So again, a new model is trained to predict which sources will be photos the outliers, and then then you go down the two branches and they get combined. But essentially, the idea is to remove photos the outliers, which are going to, let's say, mess up the models in some way. So as you can see from this table at the bottom, compared to the Clark et al. Paper, which was essentially what we were using for a benchmark, the results are almost always better, significantly. Of course, they're already very high, so a small change is happening, and it's never going to be possible to get to 100%. But the method looks very promising, and you can speak to Pedro more about this in the machine learning club. So next, very briefly, something which we recently published as a proof of concept is making use of unlabeled data when you are trying to derive redshifts and physical properties. So I mean, the idea is that when you have say, just thinking about Euclid, you might have, say, a very nice deep survey area, which is basically like a small, say, well, it's like a pencil beam, I guess, more or less, maybe a bit bigger. And you don't have a full picture of what the overall population of galaxies and sources is like in the universe. This can be just because rare sources are missing, so so rare, or because of some variance, basically, between different patches of sky. So we were thinking, wouldn't it be great if we can somehow grab information from what we expect to be a very large amount of unlabeled data and find a way to pull some of that information into the model and then improve the predictions that we make on that unlabeled data. So this is something which it's used in online machine learning competitions for years, but I didn't see it in astronomy yet. It seems very relevant to what we do. So the concept is you start off with your labeled data, you train a model, then you make predictions on this larger set of unlabeled data. Then what you obtain are pseudo labels. These are labels for the unlabeled data, which are not the ground truth, but they're produced by the model predictions. And then you basically put together the labeled data and the pseudo labeled data. So you have a bigger data set. Some of it is from your test set, some of it's from your original training set. And then you train a new model on that new combined data set. And you predict new labels, new pseudo labels. You take the pseudo labels in your in the right part of the data set. And you keep going until you get what you think is convergence. Then, of course, you evaluate the metrics. And it's something which sounds like it shouldn't work, because you should just be adding noise, but actually it does. And so here I'm showing so this is just for photometric redshift. I'm showing the NMAD, the outlier fraction, the bias metrics, the 3 different learning algorithms. And along the x-axis, you have the iteration number. So iteration 0 is the first model, which is only trained on the training data, every subsequent iteration is using this pseudo-labeled data, which is gradually being updated. And what you can see very clearly is that, so looking at the test data, which was used for pseudo-labeling, there's usually a very sharp and quick decrease in the metric, so an improvement in the model quality, which either plateaus or, say, bounces, then you start to overfit later on in some cases. So clearly, the model is learning about the structure of the test data, basically, or the structure of how galaxies within the overall sky are actually distributed and clustered in terms of properties. So there's clearly useful information to be extracted there. What was more surprising is that when we apply the same model to holdout test data set, so this is data which has never been seen before, it wasn't used in pseudo-labeling, we still get an improvement. So the generalization is improving as well. So I mean, this is something which seems very promising and very relevant to future surveys such as Euclid, where we'll have a vast amount of unlabeled data to work with. And then finally, something which is, I guess, sort of related. One of the things that we often do when applying or testing machine learning methods in astronomy is we assume that your training data and your test data are drawn from the same population, basically, that there's no shifts or differences between the composition of your sample. But the truth is that there always are. And also, if there are shifts, then you will have unexpected changes in model performance. So I set out to investigate this by doing something very simple. I just basically downloaded photometry for SDSS sources, stars, galaxies, and quasars. They all have spectra. We know what they are. And then to induce this population shift, I sorted them by RA. So basically, what you're doing is you're looking along RA, and some places you're looking through or at more or less the Milky Way, and some places are not. So of course you can see here a very big increase in the fraction of stars, and also a change in the median colors of the different three different classes. So of course there's reddening going on and other stuff. So imagine if you trained a model, say at RA 200, and then you try to predict the classes at RA 300. Doesn't seem likely that the same model will actually work. But that's an extreme case. There are also very gradual drifts in, say, the composition of the sample, which you might not have noticed. So I used something which was developed by my friends in tech sector. So this is open source. You can go and look at it at NanoML. It's on GitHub. What I've done here is I've trained a model. You probably can't see, I'm sorry, the shaded area in the middle between RA 150 and 200. Well, that's basically where I trained the model. And then I predict the classes. Well, I predict. No, this is just for quasar detection. So I've made a one versus all to predict whether an object is a quasar or not, basically. And you see the performance in blue varies very significantly across along the x-axis. So as you expect, when you get close or you're looking at the Milky Way, it's much harder to identify quasars. No surprises. But if we use this CVPE method, it tells us that the model is actually degrading in performance in those regions. And it's also detecting a lot of the small ups and downs in the flat areas as well. And basically what it's doing is looking at how competent the model is in its predictions. Basically, that's what it is. And so again, this is kind of, it's just a small proof of concept, but it's very interesting in terms of how this may alter the way we tune our models. Because imagine you have your say some deep field observations in one area of this plot, but you want to make a model which you can apply to everywhere else. Maybe you want to tune the parameters so that the model you produce works well across the whole range, or train a separate model which you think is going to work better, for example, at R rate 100, whatever. Yeah, and so I think there are probably good applications for it. I mean, you could also use it for selecting a survey area where you think a model will perform better, for example, because you might just think, well, we do actually want to have good classifications for objects. Anyway, that's the final slide. So summary conclusions. So as you can probably guess, my opinion is that machine learning is very promising for selection of quiescent galaxies, classification in Euclid with the expected data. Combining different machine learning methods using stacking methodologies can give us really significant improvements in model quality. And so machine learning or supervised learning, as we applied it, can generally outperform color selection and also LePhare technique, at least for the specific cases we've tried here. We're also testing machine learning methods to estimate galaxy physical properties. Again, from similar data sets focused on Euclid. And we found that trying to model or project different properties simultaneously can lead to significant improvements. We also have a low-cost method to estimate the 68% confidence intervals from these estimates, which is, I think, at least something which is better than nothing. And then, well, things I just talked about. So pseudo-labeling, I think, is a very promising method going forward with surveys like Euclid, because it allows us to get information from unlabeled data. And yeah, I mean, I also find it very promising, maybe not for me because I'm moving on to something else, but being able to estimate model performance without ground truth should find some interesting applications in large surveys. Okay, so that's the end. Thank you very much.